Life at the cellular level is under a constant threat from a remarkably simple antagonist, the hydrogen ion. Because this single proton lacks a bulky electron cloud, its small size grants it extreme mobility. It can rapidly infiltrate the deepest layers of our cellular architecture. Once inside, it seeks out molecules bearing negative charges. It binds to the structural proteins that hold our cells together and the active sites of enzymes that drive our metabolism. When a hydrogen ion attaches, it physically warps the protein's conformation. This destroys the shape required for biological function and neutralizes the enzyme. This threat is continuous. Every day, your body's oxidative metabolism produces up to 20,000 millimoles of carbon dioxide, a massive source of potential acidity. If that acidic payload were left unchecked, it would denature cellular proteins in minutes. Preventing this systemic collapse is the singular purpose of pH homeostasis. To prevent widespread protein denaturation, the body maintains a narrow survival window. If arterial pH drops below 6.9 or rises above 7.9, the internal environment is generally incompatible with life. This table defines the normal triad, the baseline metrics the body fiercely defends to maintain an optimal pH of 7.4. The pillars of this balance rely on keeping carbon dioxide at 40 millimeters of mercury and bicarbonate at 24 millimoles. Maintaining these exact numbers requires treating acid-base balance as a strict input-output equation. Because our dietary intake of metabolic base is limited, survival depends almost entirely on our ability to eliminate excess acids. We can prove this relationship mathematically using the Henderson-Hasselbalch equation. This formula demonstrates that pH is directly linked to the ratio of bicarbonate to carbon dioxide. With minimal base coming in, the only way to manage the constant acidic byproduct of cellular respiration is to rely on specialized organ systems. They act as exhaust valves, venting out acidic pressure before it builds. This timeline visualizes the body's three-tiered defense hierarchy, the BVK system. It initiates with an immediate spike from chemical buffers, shifts to a high plateau from ventilation in minutes, and concludes with a slow rise from the kidneys over 48 hours. The chemical defense intercepts hydrogen ions the moment they appear. The primary tools here are the extracellular bicarbonate carbonic acid system and intracellular buffers like hemoglobin, but their capacity is easily exhausted. Once the buffers are saturated, rapid respiratory control takes over. By hyperventilating to eliminate carbon dioxide, the lungs handle roughly 75% of the body's necessary compensatory response. The heavy lifting is finished by the slow but essential renal response. The kidneys excrete lingering hydrogen ions and reabsorb bicarbonate, managing the final 25% of compensation during a cycle that peaks at 48 hours. This graph illustrates a flaw in our fastest physiological defense. The ventilatory response is not infinite. As carbon dioxide accumulates, the curve drops off and blunts when PCO2 reaches 100 to 150 millimeters of mercury. If PCO2 approaches 200, the system collapses. The patient loses consciousness, the ventilation rate decreases, and the respiratory drive may stop altogether. The lungs offer the fastest major defense, but their inherent tolerance limits mean they cannot fight an endless battle. Any prolonged acidic attack must ultimately be solved by the kidneys, or the patient dies. As these organ systems struggle to manage the acid load, a secondary consequence emerges that can trigger fatal arrhythmias. Shifts in pH force the widespread displacement of potassium. During alkalosis, as hydrogen ion concentration drops, potassium enters the striated muscle cells. Conversely, during acidosis, a high concentration of hydrogen pushes into the cells, forcing potassium out into the bloodstream. The clinical AK rule provides a formula for tracking this shift. For every 0.1 unit decrease in pH, serum potassium rises by approximately 0.5 milliequivalents per liter. Capturing these delicate metrics requires rigid pre-analytical rules for blood gas sampling. The draw must be arterial, collected in a heparinized syringe, with no air bubbles, verified by an Allen test, packed on ice, and delivered rapidly to the lab. A single error in sampling ruins the data. A clinician cannot accurately interpret a patient's serum potassium levels without first knowing their pH. The two metrics are entangled. Acidosis originates from two distinct mechanical failures, either a failure of ventilation or a failure of metabolism and excretion. Respiratory acidosis is a mechanical issue. Decreased alveolar ventilation directly causes carbon dioxide to accumulate in the blood. Metabolic acidosis is an issue of capacity. It occurs when the input of hydrogen ions from nutrition or cellular metabolism exceeds the kidney's ability to filter and excrete them. The plasma anion gap provides the quantitative evidence required to deduce the exact cause of metabolic acidosis. It calculates the difference between measured cations and measured anions. If the anion gap is normal, under 16 millimoles per liter, the acidosis is driven by direct bicarbonate loss, such as diarrhea, or by excessive chloride intake. But if the gap is elevated above 16, the scale tips. The acidosis is driven by an influx of unmeasured acids, like lactic acid from shock, or ketone bodies from diabetic ketoacidosis. Recognizing whether an acidosis is respiratory or metabolic dictates the entire clinical response. It identifies whether to fix a blocked airway or filter the bloodstream. While less common, alkalosis is just as destructive. It disrupts the Henderson-Hasselbalch ratio by depleting acid or hoarding base. Respiratory alkalosis is the consequence of hyperventilation that is not driven by the body's actual carbon dioxide production. Instead, panic, altitude, or disease leads to excessive respiratory elimination. Metabolic alkalosis begins when bicarbonate concentrations exceed 28 millimoles per liter. This is often the result of severe vomiting, which drains hydrochloric acid, or the use of diuretics. This section highlights a weakness in our defense against metabolic alkalosis. As the warning box states, respiratory compensation is limited because human tolerance to hypercapnia is low. The body cannot safely stop breathing to retain enough acid to balance the scale. As a result, metabolic alkalosis leaves the patient with virtually no rapid compensatory safety net. How is it possible for an intensive care patient to show a normal pH of 7.4, yet be moments away from cardiovascular collapse? This stability is often a facade, created by complex acid-base disorders. These occur when two separate primary disturbances hit the body simultaneously, masking the physiological crisis. This logical scheme outlines the danger. Under same direction, simultaneous disorders cause extreme, uncompensated pH. We see this in mixed acidosis, decreased pH, increased PCO2, collapsed bicarbonate, which is fatal within minutes. But in opposite direction, opposing disorders cancel out, making the pH appear normal. Trusting a normal pH reading in an acute setting without cross-referencing gas and electrolyte values is a catastrophic diagnostic error. The equilibrium is an illusion. This brings us to a final clinical mandate. A standalone pH value is never enough to determine a patient's physiological safety. To uncover these hidden pathologies, you must execute a synchronous analysis of the entire panel: pH, PCO2, bicarbonate, potassium, chloride, and the anion gap. True pathophysiology cannot be reduced to a single decimal point. It requires visualizing the entire biochemical picture, the constant interplay between the lungs, the kidneys, and the cellular buffers. That interplay dictates an immutable law of critical care. You must look at all parameters together. Understanding these simultaneous pressures allows a clinician to look past a stable pH and address the actual underlying crisis.